Hello, this is Juno Kim presenting the first report for Group 5 in Professor Hong's Mechanical Engineering Creative Design class. Here is the order of contents for today's presentation. We'll be focusing on the base case analysis, premises that could be established from the base case, and then finally the modeling equations we derived to optimize problem solving. In the global search to find cleaner energy solutions, lithium-ion electric vehicles have risen as a dominant replacement for gasoline cars. Among the many issues that need to be solved for the popularization of EVs, battery pack efficiency improvement and effective thermal management of heat will be the main focus of this class. Thermal runaway may happen from loss of control, which can even kill passengers. In order to intelligently create the optimal cooling pipe design, we tried to construct appropriate modeling equations that will provide a relationship between design parameters and the KPI scores. Examples of design parameters are pipe diameter, number of division paths, and individual branch lengths. 5 key performance indexes were given for this project. The first KPI is the standard deviation of temperature differences between each of the 6 cells in the battery pack. Lower standard deviation of temperatures would result in a higher score because each cell generates roughly the same amount of heat during operation. Because the coolant can flow in only one direction from inlet to outlet, areas near the inlet will meet the coldest coolant, while the outlet areas will meet the warmest coolant. The net energy index is evaluated by the battery's electrical energy production minus the pumped compression power in circulating the coolant. The volume index exists to prevent each teams from making the module housing size unrealistic large to dissipate the generated heat. Also, it would be nicer to have a larger EV cabin room achieved by smaller batteries. The temperature KPIs reflect the optimal temperature range to maximize lithium battery performance, which is between 10 and 30 degrees Celsius. The different weight factors allow the variations in each of the 5 KPIs to have similar contribution in the total score. Here are the key thermofluidic equations we will use to construct our models. Fourier's law, Newton's law of cooling, Reynolds number, and Poiseuille's law are included. We now move on to the base case analysis. Base case analysis is conducted for the purpose of finding reasonable grounds to build simplified modeling equations. Analysis is divided into thermal and fluidic sections. The information of interest are the heat transfer profiles from cell to adjacent space, into the coolant pipe buried in metal housing, Reynolds numbers, full profile, and pressure drop. The first analysis is the thermal conduction in the cell and to the space between them. To understand heat transfer from the cell to the adjacent space, we drew an electric resistor model that juxtaposes conductivity and thermal resistance. In it, the coolant housing will be on the right side of the black and green rectangles. This could be done because the 6 cells in adjacent spaces are placed in series. We can assume that the cell and the empty space as a thermal resistance network, represented by the equation on the right. So when the cell generates a steady heat flux, decreasing the thermal resistance will decrease the temperature difference between each ends of cells and spaces along the x-axis, which will increase the KPI score. The reason why we prioritize conduction here is because we will later consider inserting cold plates between each cells in the empty spaces. The second analysis is the heat transfer into the coolant pipe buried in metal housing. Unlike conduction along the x-axis, circular pipe buried in metal coolant housing is a two-dimensional problem. We can imagine the coolant pipes placed inside the metal housing to be pipes buried underground. Heat transfer happens according to the first top equation. In it is S, the conduction shape factor. The equation for S in pipes buried in the ground is shown above. For the W term, which appears at both numerator and denominator, we graphed it and confirmed its similar behavior with the other variables. The pipe's number, length, diameter, width between, and distance from the cell are positively related to thermal transfer and thus the KPI score. The third analysis is the coolant's flow characteristics. By finding the Reynolds number, we can classify the flow to be laminar or turbulent. In the base case, the RE was under 164, which is small enough to be laminar if these numbers from ANSYS simulations were correct. However, given the mass flow rate of 0.1 kg per second, small pipe diameter, and EGW density, the Reynolds number should be over 9600, which is definitely turbulent flow. We decided to trust the reliability of velocity data because velocity is the lower dimensional term which is less likely to be disturbed. Also, from the coolant flow radial picture, the temperature is uniform throughout the radial cross-section, which suggests turbulent flow over laminar. The fluid boundary layer could be a developing flow or fully developed flow. Their boundary is called entrance length. Entrance length of the base case is shown in the right. The base case entrance length is 0.11 meters, which is much smaller than the pipe length of 0.29 meters. We cannot assume the whole coolant flow to be fully developed. However, if the coolant inlet had a longer entrance externally, fully developed flow could be supposed. We will decide accordingly for ANSYS calculation afterwards. The last analysis is pressure drop. When a fluid travels through a pipe, it experiences pressure drop due to friction. Pressure drop is necessary to get the compression power in the net energy KPI. Because V and I integral is almost constant, compression power must be infinitized to increase the total score. Compression power is a change in pressure between the inlet and outlet, which is caused by two losses. Major loss occurs from the friction between a fluid traveling inside a tube. Major pressure drop can be represented by the Darcy-Weisbach equation. Among other options, we chose the Colebrook-White equation to find the friction factor. Minor loss occurs when the fluid travels through some curvature or at connecting bumps between the pipes. Looking at the relationship between K and RE, we found that the geometrical profiles of pipes is the dominant factor for minor loss. From the base case analysis, we can obtain four reasonable premises or observations to use for our modeling. The first is the steady-state premise. Although the battery operation profile is naturally dynamic, it can be seen to have piecewise steady-state conditions for short periods of time during stable operation. In the lecture-provided voltage graph, the curvature is fairly smooth. The second is the coolant turbulent flow profile. The base case flow rate is very fast for a narrow pipe diameter. As expected, the calculated Reynolds number was over 9,000. The third is the near identical thermal profiles between the 6 individual cells. This was concluded by observing the actual temperature profiles of 6 cells in the base case. Moreover, the cells are placed symmetrically in series. The fourth is temperature and flow velocity consistency in the pipe's radial cross-section plane. This is possible because of the turbulent flow, which causes the coolant particles to mix quickly and evenly while traveling in the axial direction. Also, by the mass conservation law, mass is conserved in the axial direction, and if cross-sectional area is unchanged, velocity should be maintained. The final section is model construction. As we mentioned earlier, the objective for analysis and interpretation was to find optimizable functions that will connect the design parameters into the KPIs. We followed the four following steps. Writing governing equation for the real situation, applying premises from the base case, creating a simplified solvable model, and then verifying the models with ANSYS Fluent. We will discuss the modeling in four major directions: battery housing, coolant fluid, and coolant pressure drop. First is the thermal balance equation for the battery housing. By the premise of steady state and temperature uniformity among the 6 cell surfaces, the widthwise difference is negligible. Hence, we can simplify the case with a small slice of the surface and solve it lengthwise only. Assume the heat source is distributed evenly and consider conduction through the surface and convection to the ambient air. On the left side, the model is an ordinary second-order differential equation whose generic analytic solution becomes a lower equation. For verification, the model's prediction and the simulation result will be compared while restricting sensitive physical constants such as the thermal diffusivity and convection coefficient, and check if the solution could be numerically solved for boundary conditions. The sensitive values of alpha, H, and ambient T are fixed on the right because they often cause an explosion of the optimizer. Numerical fitting is conducted for C1, C2, and the remaining constant part by using the Nelder-Med method. The loss function is the mean square error between the 3 data points extracted from the reference result. The final result on the bottom right is quite similar to the simulation curve in blue, so the model seems suitable for modeling. The second model is about the coolant housing. The coolant housing is a solid metal governed by the thermal balance equation on the top left. For the inner volume, there is no convection, radiation, or heat source. Moreover, the design of the base case and the future design is largely symmetric or uniform throughout the battery arrangement or radial direction of coolant flow. Using the turbulent flow and cross-section temperature uniformity premises, the equation could be simplified as the left bottom second form. XEQ is the distance between coolant housing cells junction and coolant housing junction. The general solution is the bottom one with temperature and heat flux as boundary conditions. The simulation result on the right is quite linear, so the model is valid. However, the non-uniformity of relative temperature difference of cell side boundaries must not be forgotten. The third model is about the coolant. It is governed by the fluid Navier-Stokes equation and the thermal balance equation. By the premises of steady-state condition, turbulent flow, and uniform temperature in the radial plane, temperature may be considered as a function of the length variable. The resulting model is a second-order ODE with respect to x, which is analytically solvable. The general solution of the equation is on the bottom right side. Model fitting for the general solution did not converge. However, the causes were clear from Q dominance, small exponential term, and tiny differences of target distribution. The final model is about the pressure drop of coolant. The net energy KPI depends on the coolant circulating loss, which is defined by Bernoulli's equation with the loss term. For verification, the model's predicted pressure drop was compared with the base case simulation. The reference value has been calculated from the base case simulation with the area weighted average of the inlet and outlet on the right side. Since the velocity is relatively fast, flow is underdeveloped for a large portion of the length. ANSYS also showed an error in calculating the Reynolds number previously, so further study is required. In the past few weeks, we studied the design constraints of thermofluidic governing equations for designing cooling mechanism for the EV battery cells. In the coming weeks, we will refine submodels and boundary conditions, get fully analytic model of design parameters, utilize the atom optimizers, use CAD software and ANSYS design modeler to create the first sketches, and continue with the numerical simulations. Thank you for listening.